Hi, this is Dr. Collins Jones again, and this is segment 2 of my quick review of Solution and Dilution Lab Math video series. In this segment, we're going to discuss concentration calculations. We're going to give an example of how to calculate each different concentration unit. The thing that I want you to focus on in this unit is that there's actually a pattern that you can use to calculate each different type of concentration. It doesn't matter what the numbers are, but what you have to do is be consistent in how you identify the steps that you need to employ to solve the problem. So let's get started. Right? For problems involving solution concentrations in our biotech program, we often need to calculate the number of grams or the number of milliliters of solute in a specified volume in order to prepare a specific solution. We prefer to work in the units of grams or milliliters because those are the units of the equipment in our lab. Right? Our balances are calibrated in grams. Most of the volumetric apparatus is in milliliters, right? Our graduated cylinders, our serological pipettes, and so forth. The balance doesn't have a nanogram setting, at least ours don't. The graduated cylinders, the volumetric flasks, the serological pipettes are calibrated in milliliters. The only exception to this is the micropipette men, which are calibrated usually in microliters. Okay? So let's just look at the equations that you would use to do the types of calculations that we need to do. And again, the idea here is this is an equation that you can use once you identify which version of concentration, molarity, percentage, mass per volume, you need to use, then this is the equation that you can apply. So for molarity, remember, molarity is defined as moles per liter, right? And moles is given by grams divided by molecular weight, right? And moles is given by the lowercase n. So MW is molecular weight. In modern times, we sometimes use MM as molar mass, and in really older times, we use FW, formula weight. They're all used interchangeably. MW, MM, and FW are all units of grams per 1 mole. So we can use those interchangeably. And I would remind you that you can look up the molecular weight of a molecule on the web, right? Just type in molecular weight of whatever the molecule is. And oftentimes you can just type it in as the formula or as the chemical name if you know the chemical name. A lot of times the molecular weight is printed on the label of the reagent bottle. It's usually on the side or sometimes right underneath the name of the compound. And that's why I include, besides molecular weight and MM, a lot of times they haven't changed the label format for literally 50 years. And so 50 years ago, they often used formula weight instead of molar mass or molecular weight. But they're all, again, the same. And so those are the ways that you can determine the molecular weight, or if all else fails and you know the chemical formula, using the periodic table and the atomic weights of each element in that molecule, you can manually calculate the molecular weight. Okay, so that being said, the molarity formula then translates to grams divided by molecular weight, because moles are grams over molecular weight, times liters. Usually we want to find grams, so to find the grams, we take the molarity, multiply it by the liters, and the unit is important here because we do molarities in moles per liter, so the volume needs to be in liters as well, times the molecular weight. So it's molarity times the volume in liters times the molecular weight. If we look at percentages, remember a percent can be a percent weight volume or a percent volume volume. So for weight volume, the grams, that if we need to calculate the number of grams to prepare a certain volume of solution, it's the volume to prepare in milliliters times the grams, which is really the percent. So if it's a 12% solution, it would be 12 grams divided by our unit volume, 100 mils. So again, it's the volume to prepare, and it must be in milliliters, times the grams, which is really the percent value, divided by 100 mils. Okay? For the percent volume, it's very similar. The number of milliliters is the volume of solution that you want to prepare times the milliliters, which would be the percent, So if you wanted to make 70% isopropyl alcohol, it would be 70 mils divided by 100 mils. Okay. And then for mass over volume, of course, this is an infinite number of combinations. But for example, the number of grams would be the volume to prepare times the mass over volume. All right. And as an example of this, suppose we wanted to do grams as volume to prepare, and we're preparing the volume in milliliters, so it'll be times grams per mil. And so the important point here is that the volumes must have the same unit. And in this case, it's been milliliters. But in other cases, it could be microliters and microliters. But the idea here is that the volumes will cancel out when you put the information into the equation. All right, so here's the pattern that I kind of recommend to consider when you solve a problem. If you use the same series of steps every time, it sort of automatically commits to memory, and it gives you a little template, a little guideline that you can rely on. Even if your mind temporarily goes blank, you just start following the steps, and if you've done enough practice problems, then the next step will come to mind. So the first thing that we're going to do is identify each component in the solution. All right. Treat each component individually as if it is the only component present, and solve each component as a separate problem. Remember, as you read this problem, you need to also pay attention to the units, grams, milliliters, liters, microliters, whatever it is. You always need to be aware of the units. Okay, so we've identified each component in the solution, and now we're going to treat each component as if it was the only thing present. Okay, next, identify the volume to be prepared and the unit for the volume. Right, and if we need to, adjust the volume so that it corresponds to the concentration formula. So liters for molarity, milliliters for percent. Identify the unit of concentration associated with each component. And once you know that unit of concentration, identify the formula required based on the unit. So, and if the concentration is in molarity, then you're going to need to use a molecular weight. So you will need to determine the molecular weight. If moles are not involved, then the molecular weight is not needed. Even if the molecular weight is given in the problem, but the problem is a percentage problem, you do not need the molecular weight. Then determine all the volume, all the values, the volume, the concentration, molecular weight. Determine all the values associated with a specific component, and then just plug them into the formula for that component. Convert any prefix units as needed before you do the calculation, and then just do the calculation and remember to use the proper number of significant figures in your final answer. And I will have a lab math video in the measurement significant figures and data analysis unit on how to determine and do arithmetic operations with significant figures. Just as a quick reminder, I'm not going to read through all of these, but if you want to, you could you could stop the video at this point and write these down. But this is how we convert or interconvert liters and milliliters and milliliters and microliters. Okay, and this should be something that you are quite comfortable with by the time you complete whatever program you are in. And then the same thing for grams to milligrams or milligrams to micrograms, right? And then also occasionally we do molarity, and we do that in terms of millimolar or micromolar, right? If you are working at a large scale, you will also need to be familiar with grams to kilograms and kilograms to grams. But you see the pattern here, so hopefully this will be useful in helping you be able to figure that out for other unit combinations. Okay, now let's do an example. Okay, calculate the molarity of a sodium chloride solution prepared by dissolving 24.2 grams of sodium chloride in 250 mils of UP water, and that just means ultra pure water. That's our 18.2 mega ohm, less than less than or equal to 10 parts per million total organic carbon water that we mentioned in the first segment, the water that we use to prepare aqueous solutions. So we go through the steps. We're going to identify the component. We're going to identify the units and the values associated with each component. So we see that we have molarity, we have grams, and we have milliliters, which is volume. So for molarity then, if we have molarity, we're going to need the molarity equation. Molarity is equal to grams of NaCl divided by the molecular weight of NaCl divided by the liters of solution, right? So now we just need to figure out what component is where. First thing we're going to do is we notice that we have a volume in milliliters and molarity is expressed in liters. So we're going to need to convert milliliters to liters, right? And here's our little conversion factor. So we now have 0.2500 liters. And you're going to have to keep this in mind because if you enter this into your calculator, unless your calculator has a fixed significant figures option, this most likely will be displayed on the screen as 0.25. And the 2 zeros, even though they're there and significant, the calculators usually don't care, so they just drop it to save memory space. So again, we have molarity. The volume is given in milliliters. We need to convert it to liters. Okay. We can obtain the molecular weight of sodium chloride once again by looking it up on the internet, by reading the formula weight or molecular weight on the reagent bottle, that is the bottle that NaCl was supplied in, or we can manually calculate it using the atomic weights for sodium and chlorine. So now that we have this information, we have the grams. Okay, so we can plug this into the equation. 24 grams of sodium chloride, that's the grams of NaCl. The molecular weight, which we again looked up on the internet, and the volume, which we converted from milliliters into liters, and now we just carry out the calculation. That's the display number that my calculator gave, but we know that that's too many digits. And so when we take into account significant figures, the final answer is 1.66 molar, and we have 3 significant figures. Okay? All right. Now let's do percent. Let's calculate the percent of an SDS solution prepared by dissolving 18.0 grams of SDS in 1,000 mils of ultrapure water. And notice I'm just sort of changing the wordings here a little bit to get you used to the idea that different people may express this different ways. Right? If I did everything consistently, this would be dissolving 18.00 grams of SDS in 1,000 mils of UP instead of U period, P period water. But different people say things differently, and I just want you to sort of take that into account. All right, so this is a percentage problem, right? But we have grams and we have milliliters. And if you remember, milliliters is the unit of volume we want for percentage. So this is grams. So this is going to be a weight volume problem, right? We have grams here. So this will be a percent weight volume, and that's going to be grams of solute over the mils of solution times 100%, or 18.00 grams of SDS over 1,000 mils of water times 100%, or this is 1.800, okay? And we're going to assume that these zeros are significant because presumably you would make this up in a 1 liter or 1,000 mil volumetric flask, okay? One thing I want to mention here is that SDS is an irritant. It's considered a hazardous chemical, and if you get it in your eyes or in your nose, it's going to irritate those membranes. So be sure to wear appropriate PPE, and if you need to weigh this out, weigh it out in an appropriate environment, usually in a chemical fume hood. And sometimes we also include a face mask, an N95, or even a respirator. All right, our next problem. Calculate the percent volume of a Triton X100 solution prepared by dissolving 500.0 microliters of Triton X100 in 50.0 mils of UP water. So Triton X100 is a detergent. It's a water-soluble detergent, and it helps dissolve molecules that may not want to dissolve in an aqueous solution. So Triton X100 is a non-ionic detergent. SDS was an ionic detergent, but Triton X100 is a non-ionic detergent that helps us dissolve molecules that have some hydrophobic, that is, some water-fearing properties. Okay, now it says 500 microliters of Triton X100, so we know that this is supplied as a liquid. Okay, and we're calculating a percentage, and here we indicated, just to be nice, that it is going to be a volume percent, and that we have 50 mils of water. Notice, though, that the units for Triton X100 are microliters. Okay, so we just put in our percent volume solution, mils of solute over mils of solution times 100%. The volumes must be the same unit, milliliters for percentage. So the mils of Triton X100, we do our conversion, and it turns out to be 0.5000 mils. And again, your calculator will probably drop the zeros to save memory space, but you need to remember this when you report out your final answer. So the percent weight, oops, I made a mistake here. Sorry, this should be percent volume, not percent weight volume, is 0.5 mils of Triton over 50 mils of solution times 100%. And again, this should be percent weight volume, not percent volume. And so the percent volume is 0.0100%, and we have 3 significant figures. And again, we'll have a separate unit and segment on how to determine the number of significant figures during your calculations. Next example, calculate the milligrams per mil of a BSA solution prepared by dissolving 0.750 grams of BSA in 800 mils of ultra-pure water. And so BSA is bovine serum albumin. That is a protein derived from the blood of cows, bovines, and it is a very commonly used protein, especially in solutions where we have other proteins and we want to prevent those proteins from denaturing. And BSA is also frequently used as a standard protein to prepare a standard protein solution for protein assays. Okay, but let's, a little bit of background there, but let's just focus on the actual calculation that needs to be done. So we have milligrams per mil, that's a mass per volume, right? We have grams of BSA, and we have mils of water. So our equation just becomes milligrams per mil of BSA is the milligrams of BSA divided by the mils of solution. This one is so easy that sometimes people try to make it complex. And this is why we want you to stick to the pattern. Trust the pattern of solutions. Okay, trust the order, the steps that you use for a solution and the formulas. And this is why I like people to always write down the formula first and then fill it in. Yes, it takes a little bit longer, but it's better to take a little bit longer and get it right than to do it as quickly as you can and get it wrong, right? In the classroom, that's points off. At a company, that could be millions of dollars. That could be a drug that doesn't get to the patient in time. So always double check your calculations. Always do them in a nice, linear, stepwise fashion so that you and anyone else can follow your calculation process. So BSA has to be expressed in milligrams. So we're going to convert the grams of BSA that we were given to milligrams. And here's the conversion factor. And now we just need to plug this into the equation. We calculate this out, and our final answer is 0.938 milligrams per mil. Again, 3 significant figures, right? We have 3 significant figures here, right? And these zeros may or may not be significant, but we're going to have to assume when we prepare things in the lab that those zeros are significant unless otherwise stated. Okay, and that is the end of segment 2, solution calculations and how to calculate concentrations.